So question 11 on the revision sheet comes from 2000 higher level, question 6, so it's part of the question. The first thing I wanted us to do is state Newton's law of universal gravitation, which is that the force is directly proportional to the product of the masses and inversely proportional to the distance squared. So in the second part of the question, the calculation that I have on your revision sheet, you're asked to use this law to calculate the acceleration due to gravity, which is at a height above the surface of the Earth, which is twice the radius of the Earth. So if I was to draw a diagram, well, there's the Earth, here's the radius of the Earth. So our object is twice that radius. So that would be 2r. So in other words, the distance from the centre is 3r. Now, I know that my universal law of gravitation states that F is equal to G times M1 times M2 over D squared. So generally when we're talking about the large planet and the small planet, the mass of the Earth would be the capital M, and the small m is the mass of the object that is above the Earth's surface. So I know that weight is equal to mass times gravity. So by equating the two of those, then we end up with a way of calculating gravity. So we end up with mg is equal to g m over d squared, and our small masses cancel. So in other words, it's irrelevant, the mass of the satellite. So this is our way of finding the value of gravity. Now, I'm told that the distance of this object is going to be 3 times the radius. So if I look at gravity on the surface of the Earth, it would be gm over, there should be a capital, So we'd have capital G m over the radius of the Earth squared. So if I'm looking at the object above the Earth's surface, then it's going to be gm over 3r squared. And of course, if I square that out, then that gives me gm over 9r squared. Now, if we compare the Earth to the object, what we actually notice there is that it's 1/9 that the value of the Earth's surface. And we're given in the question the fact that gravity of the Earth is 9.81. So therefore, gravity of the object, which is twice the height of the radius of the Earth above, then it's just basically 1/9 times gravity on the Earth, which is this. In other words, 1/9 of 9.81, which gives us then a value of 1.09 meters per second squared. Okay. So the second question here that was asked was question 12, and this is still from 2010 on the higher level paper, question 6. So it was actually part of the same question. So we're asked, at what height above the Earth's surface will the astronauts experience weightlessness? And we're given the mass of the Earth to be 81 times the mass of the Moon, and we're given the radius of the Earth to be 6.36 by 10 to the power 6, and we're also given the distance between the centres of the Earth and the Moon. So of course, at some point between the Earth and the Moon, they'll experience weightlessness. So what that means is that the pull on each is going to be exactly the same. So in other words, the two forces, the force from the Earth and the force from the Moon, will be equal and opposite, and therefore the net force would be 0, experiencing weightlessness. So of course, if I sub in my values, then we have gravity, universal gravitational constant, and then we have the mass of the Earth and the mass of the Moon, and that would be over the radius of the Earth squared is going to equal to, not the mass of the Moon there, it's the mass of the astronauts, and then obviously that would be equal to G mass of the Moon, the astronauts, over the radius of the Moon squared. So we can see then that G is going to cancel, M will cancel, and then what we're left with is mass of the Earth. If I divide across there by mass of the Moon, multiply across by the radius of the Earth squared over radius of the Moon squared. Now we know that the radius of the Earth is 81 times the radius of the Moon. So in other words, the mass of the Earth over the mass of the Moon is equal to 81. Because we were told the mass of the Earth is 81 times the mass of the Moon. So mass of Earth over mass of Moon is 81. So 81 is equal to the radius of the Earth squared over the radius of the Moon squared. In other words, I can write it as 1 over the other squared. So then if I get the square root of both sides, that gives me the radius of the Earth over the radius of the Moon is the square root of 81, which is 9. So what that means is that the ratio is going to be 9 is to 1. Okay, so in other words, if I go up to my diagram there, my ratio is 9 is to 1. So therefore, the height above the Earth, if I do it up here beside this diagram, would be 9 is to 1. And therefore, the height above the Earth is basically 9/10 of that distance between the two centres. And the two centres is 3.84 by 10 to the power of 8. So if I get 9/10 of that, I get 3.456 by 10 to the power of 8 metres. But of course, that's the distance from the centre of the Earth. So therefore, the height above is just this little bit here. So that's going to be h, if I mark that on my diagram. Height above the Earth means I need to subtract the radius of the Earth is equal to 3.456 by 10 to the power of 8 minus the radius of the Earth over here on the left is 6.36 by 10 to the power of 6. Sorry, that gives me 3.39 by 10 to the power of 8 metres above the Earth. It's a really nice kind of maths question there. So linking your ratios to the distance between the two. Okay?